Hello, everyone. Thank you for joining today's Snack and Learn. My name is Kristen Navaroli, and I'm honored to present on a case study we performed for the California Department of Transportation. A little about myself. I am a water resources engineer at WSP in the Raleigh, North Carolina office. I went to North Carolina State University, and I achieved a degree in biological engineering with a focus on environmental systems. Now, I primarily focus on hydrologic and hydraulic modeling, as we're going to see today, as well as drainage design. Two housekeeping items. There will be a question and answer session at the end of this presentation. Please enter your questions within the chat box. And the presentation will be available to download within the handout box. So without further ado, we are going to go ahead and get started. So this is the pilot climate change assessment with integrated snowmelt and wildfire, the Little Indian Creek culvert assessment. Again, my name is Kristen Navaroli. And today we're going to take a look at a little bit of a project introduction, how this project came to fruition. Then we're going to take a look at the site, the location of the project before zooming into the watershed and then the culvert, taking a look at this existing facility, so the infrastructure, the roadways, before we develop our climate scenarios. Then finally, we're going to move into our climate simulations, how we use those climate scenarios before building our adaptation analysis. Then we're going to bring it all home, highlight some key takeaways, and then we're going to have our question and answer. So first, I always like to acknowledge the team of engineers, scientists, and planners who all worked on this project. This study was a testament of the brilliance we have at WSP and how diverse skill sets can come together and really make something great. Moving into some project background, back in 2018, California's Department of Transportation, or Caltrans, performed a vulnerability assessment looking at their infrastructure and how they strategically want to approach improvements. This resulted in a targeted study in District 2, focused on climate adaptation pilot studies. This project was a consequence of this effort. The goal of the project was to provide a template of climate adaptation studies that can be replicated in other similar mountainous watersheds. Taking a look at our specific project, our project site is located in Northern California, as we can see here, within the Sierra Nevada mountain range. Our culvert resides under a state road, which is a minor roadway, however, provides an important connection between communities on the east to the west side of the mountain range. And it takes on even more significance during winter months when the other mountain roads become impassable due to heavy snowfall. And as I previously mentioned, we're in Caltrans District 2. Zooming in a little bit further, we're going to take a look at our watershed. In this top right photo, we can see our watershed here. As you can see, it's a long, narrow watershed with steep elevations coming down to our channel. So as you can imagine, when it rains and that rain hits the land, it's going to move very quickly down to the channel and then proceed down to our culvert. So we have very quick flows moving through here. Looking at this left figure here, we can see some debris in the channel as we would expect for a fast moving river. Then we can also see some of this depositional material. And then we have our culvert in the state road that I mentioned previously. And we have about 20 to 50 feet of shoulder before we hit this larger river downstream, the North Fork Feather River. Zooming in even further, looking at our existing facility, we have our culvert, a reinforced concrete box culvert. Our head wall and end walls have been modified throughout the years to protect against damage, improve hydraulic performance. And the culvert has been inspected and denoted to be in fair condition. So Caltrans does not have any plans to replace the culvert, assuming no future flood damage that would take it out of commission. Therefore, our climate projections as part of this study were extended all the way to year 2099 to better understand how a changing climate is going to impact this asset. As I mentioned, it wasn't going to be replaced unless there was heavy storm damage. And as we can see, back in 2017, we had one of those heavy storms. There was significant flooding. You can see some of the damage here as we have the guardrail, damaged shoulder. There's a little bit of cosmetic damage done to the actual culvert and end walls. And this rushing river here is actually if you were standing on the roadway on top of the culvert. This is not the river itself, this is the roadway overtopping. This storm event caused about $500,000 worth of damage to this asset alone. And because it was proven by historical events that damage doesn't just happen to the culvert, but also the roadway and other infrastructure, our study expanded to encompass all of those assets. So now that the decision has been made to further study this culvert, how are we going to do that? Using the ADAP, or Adaptation Decision Making Assessment process. So the ADAP process was developed for the Federal Highway Administration. It's an 11-step process to evaluate any infrastructure type against climate stressors that might cause damage or impacts. As you can see here, we started with number 1, we understood our site context, then we moved into documenting our facility. Now we're going to move into identifying our climate stressors, building those climate scenarios, answering those important questions before assessing the performance of the facility and developing those adaptation options. So as we all know, the future is very unknown. We do not know what the climate is going to look like 20, 50, 100 years from now. So that's why we need to predict and project all possible scenarios. We cast that wide net. So we look at warm, dry climate scenarios, all the way to cool, wet, and then everything in between. Accompanying this, we're going to look at greenhouse gas emissions. Again, we want that wide net, so we're going to look at low greenhouse gas emissions as well as high greenhouse gas emissions. Through all of these different combinations, we had 8 possible climate scenarios that we looked at as part of the study. Taking those climate scenarios, we're going to look at 3 variables that most impact flooding. For this study, we're looking at rain, snow, and wildfire. Starting off with rain, an important climate variable is temperature. So your temperature is going to determine your precipitation type. Either when it rains, is it going to fall as rain, a wintry mix, or snow? And unlike rain, snow doesn't create an immediate runoff and delays your potential flooding. And then also your precipitation depth, which is the amount of water to trigger a storm event. Next, we're moving into our SWE, our snow water equivalent. So that's how much water is held within a snowpack if it were to melt. If you can imagine like that light, fluffy snow you see when you're skiing, that's going to have a very low SWE. There's not a lot of liquid water held within the snow. As compared to a slushy snow that sprays when you drive through it, that's going to have a very high SWE. There's a lot of liquid water within the snowpack. And the greater the SWE you have, the greater the flooding potential. Our final climate variable is going to be wildfires. Wildfires are becoming more and more prevalent in California, as we've seen in previous years. Burn-scarred landscapes that we can see here through this discoloration, as well as through the damaged trees, significantly increase flood and debris flows. So not only is there a loss of vegetation, fires create a hydrophobic reaction with the soil surface, limiting that infiltration capacity. So the soils start to act similar to impervious surfaces like pavement when there's runoff. Also, wildfire was used to determine to what extent the runoff and debris flow will be enhanced in that post-burn landscape. So with those 3 variables, we created 2 different hydrologic simulations. First, which being rain on snow, which is a combination of different temperatures and SWEs. So we took varying ranges of temperatures, 40 degrees all the way to 70 degrees, and we put that rain on varying depths of snowpacks. So you have cold rain on a small snowpack, all the way to a warm rain on a thick snowpack. Similarly, we have our rain on wildfire. Using area weighting, we were able to estimate how much of the watershed would burn and then manipulated the watershed curve numbers to represent this change in landscape. It's important to note, it was assumed it would take 10 years for the watershed to fully heal from the wildfire, and healing would proceed in a linear fashion, stepping down each growing season. So that being said, the impacts of the wildfire were present for about 10 years following an event. This is my favorite graph of the whole presentation because it summarizes everything we just walked through. So the black line that you see here on the graph comparing rainfall depth in inches to flow runoff coming off the watershed, the black line is a traditional rain on land scenario. There were no climate factors incorporated. This burgundy line here is your fire line. It's your burn-scarred landscape. If it were to rain on that landscape, what those flows would look like. And as you can see, they're dramatically higher than our traditional rain on land. Then these color patches like we have here in the pink, we have 70-degree snows, then we move down to 60, 50, and then these yellows are your 40-degree rain. And you might notice some of the yellow lines are below that rain on land, and that's because the snowpacks are essentially acting like a sponge. They're holding water up within the watershed because it's not melting as quickly as it did with that warmer rain, therefore delaying our runoff, changing the hydrograph of our watershed. Taking a look at a specific example, a warm and dry climate scenario, or our HADGEM. Up top, we have our low greenhouse gas emissions, and down below, we have that high greenhouse gas emissions. So I like to focus on this later half of our study, so 2070 to about 2099 in both greenhouse gas scenarios. The pink is going to be your wildfire. So we're demonstrating that stair-step healing fashion, as I mentioned before. Then in your blue, you have your rainfall depths. We still have a significant amount of rainfall. And then in green, we have our snow water equivalent. So that's falling snow. Looking down to that higher greenhouse gas emissions, we have twice the instance of wildfire. Again, proceeding with the healing in a stair-step fashion. And then we have those blue instances of rain, which are significantly higher, but you may notice there's less instance of snow. Oops. So moving into our adaptation options, we developed 3 alternatives with varying levels of investments. So we took all the way from our Band-Aid approach of slightly patching up the road, making it a little bigger so it improves slightly, all the way to our Cadillac option, a multi-span bridge. Water's never going to overtop the roadway ever again. Now, how do you decide which is the best alternative to propose to your client? That's where our economic analysis becomes involved. So taking a look at our economic analysis, we incorporated things mostly provided by the state of California to make a decision on what alternative is best. So our watershed is here where it says Belden, and our watershed's just in this area. And I mentioned that the state road connects our eastern to western communities. So if the culvert were to fail, the roadway were to go out, you would have this significant detour going around connecting you to the western community. I don't know about you all, I don't want to drive around 3 hours just to go get my groceries. So that adds value as to why we need to make these infrastructure decisions now. We also included things like looking at gas prices, gas emissions, trucking, and the extra mileage that would be adding to the trucking, and all of the other climate variables that go into an increased detour time. Additionally, we looked at a damage depth function. So over here, this is looking at the existing facility if it were to flood. And if we had a rain that caused a water surface elevation of around 2,228.5 feet, that means it's just overtopping the roadway. We're projecting a little bit of mud on the road. It's some debris, but it can take a few days for maintenance to clean it up. And there's gonna be about a 3-day outage causing this detour. And that we're looking at about $100,000 to clean that up. all the way to if we overtop the road only by 2 feet, then we're starting to look at pavement damage like we saw in that picture from 2017 to a higher extent. And we're looking at a several week outage of the roadway that this detour is deployed. And we're looking upwards of $1 million worth of damage. So it's showing that yes, there are going to be infrastructure investment costs if we do replace this culvert, but there are also costs associated with it if we do not replace this culvert. So taking a look at a few key takeaways, this study emphasized forward thinking and identifying what kind of resiliency options there are for project sites. So taking this to your work and your projects, you may not be forecasting all the way out to 2099 like we were here, but thinking about what does an investment look like 20 years from now if there are changes to your landscape. Starting these conversations with our clients allow for more future-ready solutions when making decisions about infrastructure investments. Also, this study served as a template climate adaptation study we hope to use on future projects, especially in these mountainous climates, minimizing future effort and investments. Also, we can tailor these kinds of studies to regions that have different climate variables. In my home of North Carolina, we specifically look at population and how that housing development are changing our landscape and changing our hydrology and how we're going to invest in our infrastructure based off of that. And finally, hydrology can be so much more than rain on land. We used a free software, EPA Swim, to do the hydraulic modeling within this study, and you can incorporate climate data such as temperature and snowmelt within that kind of model. And that allows us to better tailor our model to our project needs and goals. And if you're interested in learning all of the fun details that go along with this study, we did publish an article on it through the Transportation Research Record, and I've included a link here. The link is also available in your handout notes, and all of the fun details and graphs and pictures are included within that study. So without further ado, I'm going to open it up for questions.
Thank you, Kristen, for your presentation. So before moving into the Q&A period, I would like to remind attendees to enter your questions in the question box on the GoToWebinar platform, and also as Kristen mentioned, that the presentation is available to download as a PDF in the handout box on the dashboard. I will start with the first question. Can you clarify how was the site culvert selected?
Yes, absolutely. So as I mentioned in that 2018 study, California took a deeper look into their infrastructure, and this culvert, along with many other roadways and bridges, came to mind as they're in good condition. They are functioning. They're overtopping every once in a while, but they are very susceptible to climate stressors, as we noted about that snow melt. And this roadway in particular serves as a connection to two very important communities. So if a significant snow event were to happen, or wildfires that we're seeing more and more throughout the news, then that roadway is more susceptible to damage, therefore impacting the communities around it. So a lot of those variables went into deciding what kind of infrastructure they want to focus as part of this initiative.
Thank you. What assumptions were made within the study, and also how would these change with the different study sites?
Absolutely. So one major assumption we had to make, especially when working with climate data, was projecting it across the whole watershed. So when we looked at temperature, our watershed was about 5 square miles. So we assumed a single temperature throughout that entire watershed. Same thing with snow melt, even though you might not have snow falling exactly the same throughout a watershed. Looking at a different study area, perfect example is that North Fork Feather River, just downstream. That is about an 1,800 square mile watershed. You cannot keep the same assumptions, climate assumptions. You can't assume the same temperature from our project almost to this the Nevada border, you can't keep those, assume the same temperature, assume the same snow melt. So you would have to parcel it out a little more. So your assumptions would change for a much larger watershed evaluation.
Thank you. The next question is about the likelihood of various climate scenarios. Were the likelihood of various climate scenarios assessed? For example, the likelihood of warm rain on a large snowpack?
Yes, so we took a look at looking at snow, 40-degree rains all the way to 70-degree rains, and then 10-inch snowpacks all the way to 80-inch snowpacks. So we took the combination of all of those in between, and then using statistical modeling, we were able to find peak flows for each of those variables. That way we could find how each variable turned the needle and produce different results.
Thank you. The next question is, what wildfire data was used and how was it used?
So wildfire data is very interesting in that it's not provided as an output of these global climate models that we use for this study. There are several different methodologies. It's still a new study, and some of the most complicated can be all the way to dynamic vegetation models, looking at when it burns, shrubs, grasses are going to burn versus trees and other vegetation are going to burn. Unfortunately, that level of study was not available for our watershed. We would like to take a look more into those areas, but CalAdapt does provide outputs from a statistical fire modeling approach for the state of California. It doesn't consider that dynamic vegetation, however, it does provide annual fire frequencies and projects out for all of the simulations that we took a look at. So we were able to use that data and create some probabilities of how much our watershed would burn and how frequently they would under all of these different climate simulations.
Thank you. How was the larger downstream watershed incorporated into the hydraulic modeling?
Absolutely. I mentioned that we weren't able to use the same climate assumptions that we would for that larger watershed that we did for our smaller watershed. Again, our smaller watershed was about 5 square miles. The larger watershed is about 1,800 square miles. So we can't perform a similar climate analysis for something of that size under our scope of project. We were able to do a timing relationship. So we looked at what point that our smaller watershed would peak, what would the flow and what point of the hydrograph downstream would we connect to? And then we were able to look at the backwater effects of that connection of timing at our confluence.
Fantastic, thank you. We don't have additional questions, so thank you for submitting all these questions. We're at the end of our webinar session. Please feel free to follow up directly with Kristen via the contact details shown on this screen. And I would like to thank all attendees for joining today. Thank you for your time, and we hope to see you in our future Snack and Learn webinars.
Thank you.
Thank you, everyone.